We're going to pick up where we left off in the last lecture video. So let's start with example 11. So let bold x be a 3 by 1 random vector containing the random variables x1, x2, and x3. Let's suppose that it follows a multivariate normal distribution with covariance matrix given by this 3 by 3 matrix that you see here on slide 101. And you see that this is a diagonal matrix. That is because all of the off-diagonal elements are 0. The only non-zero elements, if there are any, are on the diagonal. So that's what we mean by a diagonal matrix. All three diagonal entries are non-zero. And so anyway, we want to determine the principal component coefficient vectors for this distribution. We want to give the formulas for the principal components. And then we want to determine the variances of the principal components. Now the characteristic roots of the covariance matrix are lambda 1 equal to 16, lambda 2 equal to 4, and lambda 3 equal to 2. And the corresponding length 1 characteristic vectors of cap sig corresponding to those three characteristic roots are C1, C2, and C3. So C1 has the entries 0, 1, 0. C2 has the entries 1, 0, 0. And C3 has the entries 0, 0, 1. And so these are, excuse me, are the principal component coefficient vectors. And so given a data vector, bold x, with entries with the component or random variables x1, x2, and x3 from this distribution, the principal components are given by the following. So the first principal component, y1, is 0 times x1 plus 1 times x2 plus 0 times x3. Okay, and that's just equal to x2. The second principal component, y2, is 1 times x1 plus 0 times x2 plus 0 times x3, or just x1. And then finally, the third principal component, y3, is 0x1 plus 0 times x2 plus 1 times x3, which is just x3. Now notice that the three principal components, y1, y2, and y3, are just the original variables arranged in decreasing order of variance. The variances of the principal components, which again are equal to the characteristic roots of the covariance matrix of the x variables, are var y1, the variance of y1 is equal to lambda 1, which is 16. The variance of y2 is lambda 2, which is 4. And the variance of y3 is lambda 3, which is 2. But again, these are just the variances of the original variables arranged in decreasing order. y1, the first principal component, is x2, and so we know that the variance of x2 is 16, and so that must be the variance of y1. Similarly, y2, the second principal component, is the first original variable, x1. It has a variance of 4, so we know that that must be the variance of y2. And then finally, y3 is just x3, the third original variable. It has a variance of 2, and so we know that that must be the variance of y3. So this is a kind of a special example or special case example. It illustrates the fact that if the original random variables, x1, x2, and so forth up to x sub p, are uncorrelated, then the principal components, y1, y2, and so forth up to y sub p, are just the original variables themselves arranged in decreasing order of variance. Now, when when the original p variables are uncorrelated, then the true dimensionality of the data set can therefore be determined by assessing the variability associated with the original variables themselves. We actually would not have to go through the process of extracting the characteristic roots and the characteristic vectors and so forth. So, and that again, that is the situation if the original p-variables are all pairwise uncorrelated. And so because of this, and because there's some other reasons too that we'll talk about, it's going to be useful for us to be able to determine whether the original variables are uncorrelated or not. Now, note that the original variables are uncorrelated if and only if all off-diagonal entries in the covariance matrix cap sig are 0. In other words, if and only if the covariance matrix cap sig is a diagonal matrix. Now, when cap sig, the covariance matrix for the underlying or original variables, when that covariance matrix is known, then determining whether it is a diagonal matrix is a matter of inspecting the matrix, just looking at it, and in particular, looking at its off-diagonal elements, right? And if all those off-diagonal entries are 0, then we know, or we could know then, that it's a diagonal matrix. If any one of those off-diagonal entries are non-zero, then it's not a diagonal matrix, and so we would need to go through the process of performing the principal component analysis, where we extract the characteristic roots and the characteristic vectors through a program like PrinCom, and doing that analysis. So again, when the covariance matrix is known, then determining whether it's a diagonal matrix is simply a matter of inspecting the matrix. The problem is that in real-world situations, we're not going to know the covariance matrix cap sig, and so direct inspection is going to be impossible. Now, if we have a random sample from a distribution possessing this covariance matrix, then perhaps we can use the data to make an inference, a statistical inference, regarding whether or not the covariance matrix cap sig is a diagonal matrix. So you see these two situations. If we happen to know that the true value of the underlying covariance matrix cap sig, then all we have to do is inspect it to look and see whether or not it's diagonal. But that's really never going to be the case, is it? In a real-world situation, we're not going to know the population covariance matrix. And so we cannot go through that process of just inspecting it. We have to rely on the data, and we have to make a statistical inference. And what we'll be doing then is we will be making a decision about the population covariance matrix, which we cannot see based on the data that we can see. Well, that process is hypothesis testing. And so what we're talking about here is coming up with an hypothesis test that will allow us to make a decision based on data about whether or not the covariance matrix is diagonal. And so the question is, how do we come up, or how can we come up with such an hypothesis test? Now, if you think back to your first methods classes, you looked at many hypothesis testing situations. You looked at hypothesis test for a single population mean. You looked at hypothesis test for a single population proportion, hypothesis test for the variance of a single population. You also looked at hypothesis test that would allow you to compare the means of two populations, tests that would allow you to compare the proportions of two populations, and so forth. You looked at hypothesis tests in the context of regression, simple linear regression, multiple regression. You looked at hypothesis tests in the context of ANOVA that would allow you to compare the means across two or more populations. And in many of those situations, the motivation for a test, or how a test is come up with, is fairly intuitive. It makes sense. So, for example, if we want to compare the means of two populations, we do that by comparing sample means from those two populations. And we have to get an estimate of the variability associated with the difference of those sample means. But that's the way we do it. And it makes sense to make an inference, to make a comparison of population means via comparing the sample means that we can see from the data. But now in this situation, what we're wanting to do is to come up with a test that allows us to make a decision, a data-based decision, about whether or not it's reasonable to assume that the population covariance matrix is diagonal. And for that kind of a test, for that kind of a situation, it may not be as obvious or intuitive how to even begin to come up with such a test. And that is what leads us into this next topic, which is the topic of likelihood ratio testing. And this is it's a very general approach to come up with hypothesis tests. In fact, we could use the likelihood ratio test to come up with hypothesis tests for all of those situations that we just talked about that you covered in your first methods classes. In fact, from a formal standpoint or theoretical standpoint, in many cases, that's exactly how those tests were obtained. It turns out that once you have derived the test, it can look fairly intuitive and make sense, and that's a good thing. But in many of those cases, the original approach for coming up with a test was via the likelihood ratio test. And so how does this work? What's the general idea? Well, let's look at the setup. Let's look at the framework. So let x1, bold x2, and so forth out to bold sub xn, denote a random sample from a distribution that has a PDF that we'll denote by lowercase f. And you'll remember that in our overview of distribution theory, we talked about PDFs. These are the functions that really describe mathematically the probability distribution of the distribution we're talking about. Now, x here, lowercase x, is the argument of the function, and theta, bold theta, is a parameter. And remember that when we use bolding, we're using that to denote a potentially vector valued quantity. And so this parameter theta is actually, it can be a vector of parameters. It could be a scalar, but it can also, if we have more than one parameter, then we would just put all of the parameters into this vector. So this is a very general notation. And so now we need to think about the parameter space, okay, the set of values that theta, the parameter, can take on. And we're going to denote the parameter space by cap omega, all right? And so the parameter theta is a member, it's in this set that we're denoting by omega. Now, the goal of likelihood ratio testing, of hypothesis testing, is to make inferences about theta based on the sample that we have available to us. Now, let's set up the hypotheses, and let's express the hypotheses in a very general way. And the way that we're going to do this is to identify or denote a particular subset of the parameter space of interest. We're going to denote that subset of interest by cap omega sub 0. All right? And then we're going to express the null hypothesis by saying that theta is a member, or is an element of this particular subset of the parameter space that is of interest and relevant in a particular situation. The alternative hypothesis will be the opposite of this statement. Remember that when you're setting up hypotheses, the two hypotheses are logical complements. They're the opposite of each other. And so if the null hypothesis says that theta is in cap omega naught, then the alternative would be that theta is either we can say it's not in here, or we can say it equivalently that theta is in the complement of cap omega naught. So both of those ways would be acceptable. So this is a very general way of setting up the hypotheses, stating the hypotheses mathematically. Now, how can we come up with such a test? And the approach we're going to look at is, again, called the likelihood ratio approach. And so we want to denote the likelihood function for the sample this way. Now remember that the likelihood function is just, think back to when you learned about maximum likelihood estimation, for example. The likelihood function is just the joint PDF of the data, thought of as a function of the sample, or as a function of the parameter. So associated with this sample is a joint PDF. And because this is a random sample, what that means is, when we say that we have a random sample, it means that the random variables, in this case the multivariate random variables, or the random vectors, they are independent and identically distributed. Identically distributed meaning they all come from that PDF, or they have that PDF, and they are also stochastically independent. And so in our overview, we looked at how to construct the likelihood function for the data in that kind of a scenario. So once we have our data, once it's been observed, then they're no longer varying, and we can consider that that joint PDF to be a function of the parameter, and we denote that function of the parameter this way. So the likelihood function of the parameter given the data. Now, let's let theta hat sub 0 denote the maximum likelihood estimator of theta under the restrictions imposed by the null hypothesis. In other words, this particular value of the parameter maximizes the likelihood function over that special subset of the parameter space that we have used in specifying the null hypothesis. Okay, so again, theta hat 0 is the value of the parameter. It's the parameter point in the parameter space in this restricted subset of the sample space at which the likelihood function is maximized. Now, we can think of maximizing the likelihood function over the entire parameter space, cap omega. And so we would denote the parameter point that maximizes the likelihood function over the entire parameter space by theta hat without a subscript on it. And so this is the unrestricted maximum likelihood estimator of theta. So in other words, theta hat maximizes the likelihood function over the entire parameter space. So when in using that notation and those particular points, then the likelihood function evaluated at theta hat is the maximum value of the likelihood over the entire parameter space cap omega, whereas the likelihood function evaluated at theta hat 0 is the maximum value of the likelihood over this restricted subset of the parameter space. And so the ratio of the likelihoods in these two, at these 2 points is given here. So we have the likelihood function evaluated at theta hat 0 divided by the likelihood function evaluated at theta hat. So again, we have the maximum value of the likelihood over the restrictions imposed by over the subset of the sample of the parameter space corresponding to the restrictions in the null hypothesis over or divided by the maximum value of the likelihood over the entire parameter space. And the traditional symbol or notation for that ratio is lambda. Now, let me just stop here for a second and say that's a little bit unfortunate because we've been using lambda to represent the characteristic roots of the covariance matrix. So what we have here is a clash in our notation, in our symbols. So I just want to point out and emphasize that in the context of likelihood ratio testing, a lambda like this without a subscript corresponds to the likelihood ratio. And when we have lambdas that have subscripts, that will typically correspond to characteristic roots. What makes this even more confusing is that we're going to be using lambda in both ways in this setup, and so it does or can get confusing. So you need to be careful that you understand what lambda represents in a given formulation. So I'll try to point that out, and I think it'll become clear when you see these things in context. But just be on your guard, and be aware of this. So again, this likelihood, the ratio of the two likelihoods, is expressed or denoted by lambda, and so a likelihood ratio test rejects the null hypothesis in favor of the alternative if this ratio of likelihoods is small. If lambda is less than or equal to some c, where c is chosen so that the test has a desired significance level, which we'll denote by alpha. Now, let's think about this. If the null hypothesis is true, then the likelihood ratio, or let me put it this way, the value of the likelihood over the parameters, over the subset of the parameter space specified by the null hypothesis would tend to be just as large, if not larger, than the value of the value of the likelihood over the entire parameter space. On the other hand, if the alternative is true, then the maximum of the likelihood over that subset of the parameter space corresponding to the null hypothesis would tend to be smaller than the maximum value of the likelihood over the entire parameter space. And so that's why we're looking for small values of lambda to decide whether to reject the null hypothesis. So the question then becomes, how do we determine this value c, this threshold or cutoff point that we're using to decide whether to reject the null hypothesis? Again, we want to choose this critical point, c, and reject the null hypothesis if lambda is less than or equal to c, and we want this c to be chosen so that the test has a desired significance level of alpha. So we might choose alpha to be 0.05 or 0.01, whatever makes sense in the context of a given situation. Now, in order to be able to do this, we have to know something about the sampling distribution of this test statistic, lambda. Now, the problem is that determining the exact sampling distribution of the likelihood ratio, determining the exact sampling distribution of lambda can be difficult, and in such situations, determining the exact critical point c of the test may not be possible. Now, it can be shown that under certain regularity conditions, if the null hypothesis is true, then in large samples, the sampling distribution of the quantity -2 times the natural log of lambda can be approximated by the chi-squared distribution with degrees of freedom equal to the difference in the number of free parameters specified by theta being able to roam over the entire parameter space, and the number of free parameters specified by the null hypothesis. And so this is a large sample test, all right, that allows us to approximate the true sampling distribution of lambda. Whatever that true sampling distribution is, we can approximate it with a particular chi-squared distribution, and then that allows us then to come up with critical points from that approximating chi-squared distribution. So this result can be used to come up with a large sample test of the null hypothesis that the parameter point theta is in this subset of the parameter space versus the alternative that the parameter point is not in that subset. And we can do this using the likelihood ratio test statistic. So to put this all together, a large sample test of the null hypothesis that the parameter point is in this specified subset of the parameter space versus the alternative hypothesis that the parameter point is not in that subset. We reject the null hypothesis in favor of the alternative if minus 2 times the natural log of lambda, where lambda is that likelihood ratio, is greater than the upper alpha percentage point of a chi-square distribution with a given number of degrees of freedom. The number of degrees of freedom is equal to the difference in the number of free parameters in the two situations, where the difference in the number of free parameters when the parameter point is allowed to roam over the entire parameter space, minus the number of free parameters corresponding to the statement of the null hypothesis. So this is how we're going to perform this test. It's a chi-square test. It's a form of a chi-square test. And so here's the formal test, the likelihood ratio test, that the original variables are uncorrelated. We're going to apply this general methodology, all right, this large sample likelihood ratio test methodology to the current situation that faces us. All right, we're going to use this likelihood ratio testing framework to come up with a test that the original variables are all pairwise uncorrelated. In other words, that the covariance matrix is diagonal. So a formal test of the hypothesis that the off-diagonal entries in the covariance matrix are all zero, that is, that the original variables are all pairwise uncorrelated, is given below. And again, this is a likelihood ratio test. So the null hypothesis can be specified in this way. The covariance matrix of the original variables is a diagonal matrix. That will be true if and only if all off-diagonal entries are zero, which is true if and only if all of the original variables are pairwise uncorrelated. The opposite of that goes in the alternative, and that says that the covariance matrix is not a diagonal matrix. In other words, at least one of the off-diagonal elements is non-zero, and so at least one pair of the original variables has a non-zero covariance and therefore a non-zero correlation. So these are the hypotheses that we're testing in this situation. Now, the test statistic for this likelihood ratio test in general is minus 2 times the natural log of the likelihood ratio lambda, which again is that ratio of the likelihood functions. Now, in this situation, it simplifies to something, to specific expressions that we can then use. Now, there's more than one version of the test statistic. The first, and I've got them listed here, test statistic 1 and test statistic 2. Now, the first test statistic is based on a direct derivation of the maximum likelihood estimators of the mean vector, which is unknown, and the covariance matrix, which also is unknown, so they have to be estimated using maximum likelihood. So this first test statistic is based on a direct derivation of MLEs of the mean vector and the covariance matrix under the conditions, or under the restrictions, specified in the null hypothesis, and unrestricted over the entire parameter space. The second test statistic is from the text, and what I'm talking about there, I'm referring to the one of the recommended resources of the text by Dallas Johnson. Okay, so there are two versions of this test statistic. You'll see that this part right here is the same in both, In the first, we multiply that by negative n, where n is the sample size. And in the second version, we're multiplying by, we can call it an adjusted sample size. The second version is used to give the test slightly better type 1 error rate performance. In this course, I'm not going to be that picky on which of these two you use. In fact, I'll tend to use this first one. All right. Now, let me just point out, okay, here we have lambdas, lambda hats, lambda 1 hat, lambda 2 hat, and so forth, times lambda p hat. We have those same values down here. Now, again, this is where there might be some confusion because we were using lambda in this context for the likelihood ratio itself. But now these correspond to estimated characteristic roots, and that's what we're saying here. So note that in the formulas above, these lambda hats, lambda 1 hat, lambda 2 hat, and so forth out to lambda sub p hat, these are the characteristic roots of the estimated covariance matrix, estimated over the entire parameter space of kappa omega. And sigma 1 1 hat, sigma 2 2 hat, and so forth out to sigma p p hat are the estimates of the diagonal entries of cap sig estimated over the restricted parameter space omega 0, the subset of the parameter space that is specified in the null hypothesis. And so in this particular context, these sigma hats are the estimates of the variances of the original variables computed under the assumption that the null hypothesis is true. In other words, that the covariance matrix is a diagonal matrix. And it turns out that those are just the MLEs of the original variables. Now, the approximate sampling distribution of this test statistic under the conditions of the null hypothesis is the chi-squared distribution, and the degrees of freedom of that distribution are p times p minus 1 over 2. Now that's a formula. Remember that in general, the way we get the number of degrees of freedom is to take the difference between the number of free parameters when the parameter is allowed to freely roam over the entire parameter space, minus the number of free parameters under the conditions of the null hypothesis. Now, when theta is, in this case, when the parameter vector is allowed to, well, the number of free parameters overall, let's put it this way, the number of free parameters overall is p times p plus 1 over 2. Under the conditions of the null hypothesis, which says that the covariance matrix is a diagonal matrix, then the only parameters are on the diagonal, the variances, and there are p of those. All right, and so the difference in the number of free parameters in those two situations would be p times p plus 1 over 2 minus p. And you can work that out very quickly. That turns out to be equal to p times p minus 1 over 2. So you'll see me in subsequent notes or examples. Sometimes I'll use this formula, and sometimes I'll calculate the number of free parameters by taking the difference that I just referred to, p times p plus 1 over 2 minus p. And so the rejection rule would be then to reject the null hypothesis if the test statistic, which again is computed using one of these two formulas, we reject the null hypothesis if the test statistic exceeds the upper alpha percentage point of a chi-square distribution with p times p minus 1 over 2 degrees of freedom. Now, we do need to keep in mind that this is an approximate size alpha test that is based on the limiting distribution of the test statistic under the conditions of a null hypothesis as n goes to infinity. Now, for large samples, the true type 1 error rate should be close to alpha, but for small values, this may not be true. Hence, results based on small samples should be viewed with caution. So again, this is a large sample test, just like most of the tests that we use in our previous methods classes. You'll remember that many of those tests are based on the central limit theorem, which again is an asymptotic result, and those tests are large sample tests. And so the bottom line is that if we have a relatively small sample size, then we need to exercise caution in using the results, and perhaps we can't really have as much confidence in results based on small samples. But if we have a relatively large sample, then this approximation provided by the chi-square distribution should be fairly accurate, and we can have much more confidence in those results. And the other thing would be that the true type 1 error rate, whatever it is, should be closer to alpha when we have large samples. So let's look at an example or two. And the first one I want to look at is in 5.1 of Dallas Johnson's text. And again, we used to have this as a required textbook, but it's been out of print for several years. And so you more than likely don't have a copy of this. So what I want to do is just read a description of this situation and this data set, and then we'll go from there. And so this example utilizes the data in what's called the Applican data set in the Dallas Johnson text. And so the question is, are the original variables in that data set correlated, or are they all pairwise uncorrelated? So the null hypothesis here would be that all of the variables, all the response variables in that data set are pairwise uncorrelated. In other words, that the population covariance matrix is diagonal, against the alternative hypothesis that at least one pair of those variables has a non-zero covariance and therefore non-zero correlation. In other words, that the population covariance matrix is not diagonal. And so we want to perform the test described above using a 0.05 level of significance. Now let me bring up my course website. All right, and you'll get access to this very soon. And this is where these data are available. If we go to the link course data and then follow the link to data sets for Johnson's text, then you see we have a list here of the data sets that are available. And the first one listed here is the data set referred to in this example. And so let me look at the structure of this data set. We see here that it has 48 observations. There are 16 variables. Okay, and here is a list of those variables. And then what I can do is look at a listing. Okay, and you can see here that we have the 48 observations, and it's got the variables listed across the top. And so let me just read a description of this data set, of this particular example, and then we'll go back to the notes and see what the calculations are to perform this test. So here is the description of this particular data set, and the description starts back in the second chapter of Johnson's book in example 2.1, and then it's picked back up in chapter 5 in example 5.1. So 48 individuals who had applied for a job with a large firm were interviewed and rated on 15 criteria. Individuals were rated on the form of their letter of application, which is this first response variable, FL. By the way, note that the ID variable is just a unique identifier identifying each individual. So the first response is, again, FL, the form of their letter of application. The second variable is their appearance. The third variable is their academic ability. The next variable is their likability. The next variable is self-confidence. The next variable, LC, is lucidity. The next variable is honesty. And then we have SMS, which is salesmanship. The next variable is experience. DRV is drive. AMB is ambition. GSP is their ability to grasp concepts. POT is the potential. KJ is their keenness to join. And then suit is their suitability. Each of these variables, each of these criteria were rated on a scale ranging from 0 to 10, with 0 being very low and very unsatisfactory, and 10 being a very high rating. So these are Likert scale data measured on an 11-point scale from 0 to 10, 0 being very low and very undesirable, to 10 being very good and very, very desirable. And so we have these ratings for each of the 48 applicants. Now let's go back to the notes. All right, and so let's look at the setup for this example. So the null hypothesis is that the covariance matrix for these variables is a diagonal matrix. Now again, we've got 15 response variables that we're considering, and so this covariance matrix is a 15 by 15 matrix. It's fairly large, and what we're trying to determine about the population covariance matrix here is whether or not it's a diagonal matrix. And because we don't know what the true covariance matrix is, we have to make a statistical inference based on the data given in that data set. And so we're going to assume via the null hypothesis that that covariance matrix is a diagonal matrix, and then give the data an opportunity to try to convince us otherwise. So this is how we set up the hypotheses. The number of degrees of freedom associated with this likelihood ratio test can be computed in a couple different ways. Number one, we can take the difference in the number of free parameters over the entire parameter space and the number of free parameters under the conditions of the null hypothesis. Over the entire parameter space, the number of free parameters is equal to p times p plus 1 over 2, 15 times 16 over 2, and that is 120. Under the conditions of the null hypothesis, the only free parameters are on the diagonal of that covariance matrix, and so there would only be 15. And so we subtract the 15 from the 120, and we get 105. So this likelihood ratio test is based on 105 degrees of freedom. Now, the critical point for the test is the upper fifth percentage point of the chi-square distribution with 105 degrees of freedom. All right, and that is equal to 129.92. Now let me bring up the chi-square table that I've got out on Moodle for this course. And so we have 105 degrees of freedom. We want the upper fifth percentage point for this distribution. So here we have the row corresponding to 105 degrees of freedom, and we want the upper fifth percentage point of that distribution. And so that's to 3 decimal places, it's 129.918. In the notes, when I created the notes, I was using a different table that rounded those values to 2 decimal places. And so that's why I've got that listed there as 129.92. Okay, but the bottom line is we now have the critical point for the test. And so all we have to do is calculate the value of the test statistic for the test. Now, I'm going to use both test statistics. The first test statistic turns out to be 752.45. Now, remember, let me go back here and let me bring up this formula, okay, that I'm using. Now, what we have to do is we have to first estimate the covariance matrix under the 2 conditions that we're considering. Under the conditions of the null hypothesis and overall unrestricted over the entire parameter space. And remember that these lambda hats are the characteristic roots of the estimated covariance matrix where we're estimating it without any restriction, okay? And that the denominator, the values in the denominator of this, the sigma hats, are the estimates of the diagonal entries of the covariance matrix under the restrictions of the null hypothesis. And so we have to come up with those values. And then according to this formula, we multiply the lambda hats together. We multiply the sigma hats together. We take the ratio of those 2 products. Then we calculate or take the natural log of that ratio, and then we multiply that natural log by minus n. Now again, let me just emphasize again that this is the natural log, not log base 10. If we meant log base 10, we would put 10 down in the subscript. But this is the natural log. Now, let me just remind you that of a property of logs, when you have a log of a ratio, let's say log of A over B, so that's what this form is. This we could call the numerator here, we could call this A, we could call the denominator B. So the log of a ratio A over B is equal to the log of A minus the log of B. Okay? And I point that out because that is, I've utilized that property of logs in this example in order to save space on the slide. I can't, on a slide like this, I can't put the actual values of the lambda hats, multiply them out, along with the values of the sigma hats, all shown on the page, and all that. So I have to express it in a little bit more succinct format, and that's what I'm doing here. So this 15.072 corresponds to the log, the natural log of the product of the lambda hats, and the 30.748 corresponds to the natural log of the product of the sigma hats. Okay, and so again, the log of the ratio is equal to the difference in the natural logs. And what there's some value out here, 48, again, that corresponds to the sample size. And so this is the formula that we're calculating here. And so the value of the test statistic using test statistic 1 is 752.45. And again, the critical point for this test is 129.92. And since 752.45 exceeds 129.92, that leads us to reject the null hypothesis and conclude that the covariance matrix is not a diagonal matrix. In other words, that at least 2 of the response variables, 2 out of the 15 response variables have a non-zero covariance and therefore a non-zero correlation. And again, we're doing this test at the 0.05 level of significance. And so our conclusion could be stated in a more complete way there is sufficient evidence at the 0.05 level of significance to conclude that the covariance matrix is not a diagonal matrix, that and therefore that at least two of the underlying variables have a non-zero covariance and therefore a non-zero correlation. Now we could also use test statistic 2, and if we do that, then the critical point is a little bit less. You can see that we've gone from 752.45 using the first test statistic to 645.33 using the second test statistic. But it really does not make a difference in this case because they're both much, much greater than 129.92. And so regardless of whether we use the first or the second test statistic, we come to qualitatively to the same conclusion that we reject this null hypothesis that the covariance matrix is a diagonal matrix and conclude that it's not a diagonal matrix, that at least two of those variables are have a non-zero covariance and therefore a non-zero correlation. Now let's take a minute to focus in and see where we make sure that we understand where we got these values that we use to calculate the test statistic. And to do this, I'm going to go back to the website, and I'm going to go back to the main page of my website, and I'm going to follow the link Programs and Solutions for Selected Examples and Exercises. And then once I'm there, I'm going to follow the link to the Selected Examples and Exercises from the Johnson text. All right, and then follow this link for Principal Component Analysis. Now, if we scroll all the way down, we have down here some analyses for example 5.1. And remember that what we need in order to do this test, we need we'll go back here, we need the characteristic roots of the estimated covariance matrix, estimated over the unrestricted fashion over the entire parameter space. We also need the estimates of the covariance matrix computed under the assumptions of the null hypothesis. Well, we can get all of these values from the output provided by the principal component analysis. And so let's look at this output from ProcPrintCom for this particular data set. And let me just look at the program first, and let me just show you that, let me see here. So here we're accessing the Applican data set, and then here is where I'm running, performing the principal component analysis, and I'm using the Applican data set. And you can see here that I'm specifying that the analysis variables be the FL variable up through the suitability variable. And so this is just a shorthand way of specifying all those variables, all those response variables as they exist in the data set. Okay, so now let's look at the output. And so you'll be familiar with this output. We've seen output from ProcPrintCom before. You can see here we've got the 48 observations, and there are 15 analysis variables that are used in this analysis, ranging from the FL variable, the form of the letter of application, all the way through the suitability variable. And here we have the estimated covariance matrix. And this is the covariance matrix as it's estimated in unrestricted fashion. Okay, and so this is the covariance matrix, the estimated covariance matrix, whose characteristic roots we want, okay, in order to calculate the test statistic, the numerator of the test of this likelihood ratio. And those characteristic roots are given right here. And so what we need to do to calculate this part right here, the numerator of this ratio, we need to calculate the product of all 15 of those values. To calculate the denominator of this ratio, we need the estimates of the variances of the 15 variables computed under the assumption of the null hypothesis. And it turns out that those estimates are they're the same as the diagonal entries in this matrix. Okay, the estimated variances in this matrix. And so we have to calculate the product of these estimated variances. So 7.1489317 times 3.86524823 times that value, and so forth. So you can see there's a lot of values that we have to take the product of, but this is where we get those get the values that we need to calculate this ratio. Then we would take the natural log of that and then multiply that by negative n, where n is 48. Now, again, because of utilizing properties of logarithms, we could, instead of calculate the ratio and then calculate the natural log, we could calculate the natural log of the numerator, calculate the natural log of the denominator, and then take the difference. Okay, so it doesn't matter how you do it. As long as you do the calculation correctly, you get the same thing. But this is the source of the values that we need. All right, we can get these values that we need for this likelihood ratio test from the output of the principal component analysis. Now, let me also show you. So this is example. We're looking at example 12 here. Okay, and we want to see how to calculate the value of this test statistic. And so I've done this analysis. I've utilized proc-IML in SAS. IML stands for Interactive Matrix Language. And I've used proc-IML to do the calculations that I was just describing, because multiplying those values out by hand, can be tedious. And so if you've got a computational way to do it, you can take advantage of that. And so here is the applicand data set, which we've already seen. We see that we have 48 observations. We have p is equal to 15. We have 15 response variables. Here is the sample covariance matrix. Okay, and so this is the same estimated covariance matrix as is calculated and provided in the output of proc-primcom. Here we have the characteristic roots of that estimated covariance matrix. And so these are the same values of those characteristic roots that are provided in the output of proc-primcom. And then we have the characteristic vectors. The columns give the coefficients for each characteristic vector. So each column corresponds to a characteristic vector, and the values in the rows in each column give the coefficients for that characteristic vector, which are used then to compute the principal components. Okay, now, so we've got all the ingredients we need to perform this test that the covariance matrix is a diagonal matrix. And so here I've calculated the log of the product of the characteristic roots. Okay, so that is the log of the numerator, and this is where we get the 15.072. All right, let me zoom in on that a little bit. The denominator is the log of the product of the sample variances, 30.748. And so then, that's where I get these values here. And I go further and I just calculate the values of both test statistics. I've got these formulas programmed into my proc-IML routine. And so we get 752.43 for, it's slightly different than shown here. This one's going to be a little more accurate because I'm using the full precision available in proc-IML. I'm not rounding. And then the second version of the test statistic 2, 645.32, okay, which is really the same we got there. Okay, this is a 105 degree of freedom test, and the critical point again is 129.92, rounded to 2 decimal places. And the p-values are really so small that, to probably 10 to 12 decimal places, the p-values are 0. They're, in actuality, slightly bigger than 0, but not much. So there's very, very strong evidence here, based on this test, that the population covariance matrix associated with these response variables are not diagonal matrices, that at least 2 of the variables have a non-zero correlation. Now, before we move on to the next example, I want to point out that this is a very important type of test for us to be able to use in the context of multivariate analysis. In those situations where we want to determine, are any of the variables correlated? Do any pair of variables, does any pair of variables have a non-zero correlation? Now, when we talked about correlation analysis in that very short module on correlation analysis, remember that we pointed out the fact that as the number of response variables gets larger, the number of correlations among those variables increases very quickly. In fact, it increases quadratically as p increases. And when we are wanting to ascertain or test hypotheses about whether or not any of the variables are correlated, we need to be very careful in how we go about doing that, because every time we do a test, there's an opportunity to make a type 1 error. And so when we are looking at, for example, when we're looking at the output of proc core, remember that proc core is going to give us, by default, hypothesis tests for every hypothesis test involving the correlation for every pair of response variables. And so, in fact, in that context, we pointed out that, for example, if you have 15 response variables, which is the number of response variables that we have here, then there are 105 tests, hypothesis tests, being performed in the output or being reported by the output from proc core. So there are 105 opportunities to commit a type 1 error just in answering the question, are any of the response variables correlated with each other? And with such a large number of comparisons, or a large number of hypotheses, even if no pair of variables is correlated, if we were doing each test at the 0.05 level, in that case, we would expect to see 5 significant comparisons, or five significant results. We would expect to see 5 pairs being indicated that they had non-zero correlations, even if, in fact, no pair of variables were correlated. And this is because with that many comparisons, the overall type 1 error rate is getting quite large. In fact, in that case, it's probably, it is fairly large. You know, could be 50, 60, 70, 80%, maybe even higher. We don't know exactly, because it depends on the relationships between the various tests, but the overall type 1 error rate in that situation can get quite large. And so we don't, in trying to answer the question, does any pair of variables have a non-zero correlation, we would not want to base our decision about that on the output from proc core, because, again, proc core is not doing anything to maintain control over the type 1 error rate for all of those tests. But this test right here that we're looking at here, this likelihood ratio test, where we're testing the null hypothesis that the covariance matrix is a diagonal matrix against the alternative that it's not a diagonal matrix allows us to answer that very same question while maintaining control over the type 1 error rate. We get to do all of those tests, all 100. This is essentially doing 105 hypothesis tests and having an overall significance level of 5%. So this gives us a strategy for making the determination are any of the variables pairwise correlated, and if so, which ones are. We can perform this test first, and then if we reject this null hypothesis and conclude that at least one pair of variables is correlated, then we can go to the output of PROC-core and see which of those pairs of variables have a non-zero correlation based on those tests. Okay, let's look at one more example, example 13. This refers to example 5.2 in the text. So the question would be, are the original variables in this data set, it's called the US Navy data set, correlated? Perform the test described above using a 0.05 level of significance. Now what I want to do is bring up the data, the US Navy data. All right, and again, it's here, data sets from Johnson's text. And let's look at a listing of the data. We see that we've got 25 observations, and we've got the first variable is a site identifier. So that's not an analysis variable, but the rest of these variables, 1, 2, 3, 4, 5, 6, 7, 8 variables are response variables. I believe that we are going to well, let me just give a description of these variables. So the variable ADO, hold on, let me back up a second here. So overall, this data set is data that's collected in an attempt to estimate manpower needs for bachelor's officers' quarters. And so the variable ADO is the average daily occupancy. The variable MAC is the monthly average number of check-ins. WHR is the number of hours spent per week. The service desk is in operation. CUA is the total common use area in square feet. WNGS is the number of building wings. OBC is the operational berthing capacity. RMS is the total number of rooms. And MMH is the monthly man hours required. Now, one thing I would point out is that these response variables all have different units. And so this is going to be a situation where it would probably be best for us to analyze the data after they've been standardized. Okay, and remember, when we standardize, that gets rid of the units, and so all of the variables are more comparable. And so we're going to do that as part of our analysis. And because we're going to get, we need the characteristic roots and and the variances and so forth of the estimated covariance matrices under the two conditions considered in the hypotheses, and we get those values from the principal component analysis. We're going to perform that principal component analysis using the standardized data. And again, if you remember from the last lecture, the way that SAS does that is to analyze the correlation matrix of the original data, because that correlation matrix is equal to the covariance matrix of the standardized data. So that's the way it's actually implemented in SAS. So these are the data that we're going to use for the analysis. And let's look at the setup here. And so the null hypothesis would be that the covariance, the population covariance matrix for these variables is a diagonal matrix, right? So that is true if and only if all of the variables, the pairwise, when we think of the variables pairwise, they're uncorrelated, against the alternative that the covariance matrix is not a diagonal matrix. And so in other words, at least one pair of the variables has a non-zero correlation. we're going to be using the first 7 response variables. We're not going to use the MMH, the monthly man hours required. We're going to use the first 7. So ADO, MAC, WHR, CUA, WNGS, wings, OBC, and RMS. And so therefore, the test is based on 21 degrees of freedom, and therefore the critical point for the test is the upper 5th percentage point of the chi-square distribution with 21 degrees of freedom, and that critical point is 32.671. All right. Now the value of the test statistic, the log of the characteristic roots of the estimated covariance matrix over the unrestricted form of the entire parameter space, minus the natural log of the product of the estimated variances under the conditions of the null hypothesis. And we'll see why this is 0 in just a second. Okay, but it turns out that the value of this test statistic is 190.225. And since that is greater than 32.671, we would reject the null hypothesis, conclude that the alternative is true, and therefore conclude that at least 2 of the variables have a non-zero correlation. If we use the second version of the test statistic, then we get a slightly smaller value of the test statistic, 158.52, but it's still quite a bit larger than the critical point, and so we would come to the same conclusion. Now let's look at where we get the values to calculate these test statistics. So again, I'm going to go to the website, and I'm going to look under Programs and Solutions for selected examples and exercises, and then follow the link to the examples and exercises from the Johnson text. All right, and all the way down here at the bottom, I have some analyses for example 5.2, and that's the example from his textbook that we're looking at, of the data from that example. And if we look at the output from Proc-Princom, okay, again, what we need are the eigenvalues, the characteristic roots of this estimated covariance matrix. We also need the diagonal entries of that estimated covariance matrix. Now, the numerator is the product of the estimated or the characteristic roots of the estimated covariance matrix, and the denominator is the product of the estimated variances. Well, now remember that we're using standardized variables, and so the way that Proc-Princom is going to do that is to estimate. It's going to calculate the correlation matrix, the estimated correlation matrix for the original variables, and then do the analysis on that. And so that's why we've got these ones down the diagonal here, because you can see that this is the estimated correlation matrix for the original variables. Now I want to point something out here. I would encourage you to calculate the product of these eigenvalues. You'll find that when you do, you get a number that is less than 1. When we take the natural log of a number less than 1, then the value is going to be less. It's going to be negative. Okay, and so we would have a negative value minus, in calculating the test statistic, we would have the log of the product of these values, which is going to be negative, and then minus the log of the product of these diagonal entries. Now, because these diagonal entries are all 1, the product is 1, and the natural log of 1 is just 0. So we would have a negative value minus 0. All right? Now, I don't want you to be confused. So this negative 7.609 is the natural log of the product of the eigenvalues of the estimated correlation matrix. And so I've just rewritten this. This is equivalent. Okay, you'll agree that negative of 0 is just 0. So instead of writing this negative 7.609 minus 0, for some reason, and I'm not sure why, I don't remember, but I just wrote that in the equivalent way, 0 minus 7.609. So you can write it either way. This is perhaps a little bit confusing, but that's why I'm taking time to explain it here. So anyway, you multiply that then by negative 25, 25 being the sample size, and we get the value of the test statistic, 190.225. If we use the adjusted value, the adjusted number of observations as the multiplier, then we get 158.52. So this is where we get the values that we use to calculate the value of the test statistic. If we go back here and look at the output for example 13, which is what we're looking at, then we have the results from proc IML, just as we had for the previous example, example 12. And actually, this particular analysis is done on the covariance matrix rather than the correlation matrix. So in this analysis, I am analyzing the original variables, not the standardized variables. So we're not going to look at that any further. But you could use proc IML to do this, by calculating the correlation matrix and then doing the calculations contained in these formulas. So we see here that in order to do these tests, these likelihood ratio tests, for testing testing the null hypothesis that the population correlation the population covariance matrix is diagonal against the alternative that it's not diagonal, we can get all the ingredients we need for that test from the output of proc PrinCom, the same procedure that we use to do the principal component analysis. And so that is why I waited to show you this particular test about covariances and correlations in this context of principal component analysis, because we get the values we need from that principal component analysis. So that is what I wanted to show you, this likelihood ratio test involving the covariance matrix. And so I'm going to stop the lecture video. It's getting quite long here. And we'll pick up. I may show you another example of this in the next video.